Welcome to APEC. It's February 26th, and I'm your moderator, Tim Ventura. I'd like to thank everyone for joining us on today's call, along with everyone watching us on YouTube. In today's session, we're proud to feature presentations by Brian Sinclair on inertial propulsion, Michael McDonough on stimulated beta decay nuclear batteries, and John Hutchison on the Hutchison effect. Mark Sokol and Falcon Space will provide lab updates for us. They have some good stuff they're going to share. And we're hoping to squeeze in Todd Desiato to update us on the Graviflyer. We'll be finishing off the event with open discussion and ad hoc presentations by conference attendees. So a couple of quick reminders. You can view conference replays, details, and speaker info on our website at altpropulsion.com. Please save your questions for the Q&A session following each presentation. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type those questions in the chat. We'll go through them after each presenter finishes. But again, it's a little bit easier to put those in Zoom using Option Y on Mac or Alt Y on Windows. So I am pleased and honored to introduce you to our first guest. Brian Sinclair is an independent experimentalist and the founder of Sinclair Tech R&D, which is focused on a variety of alternative technologies, including new work building on the inertial propulsion framework developed by Branson Roy Thornton in the 70s through the 80s. Brian started Sinclair Tech in the 90s while he was researching alternative energy generation systems and alt fuel systems for automotive applications. After building several prototypes in the alt fuel field and giving away the tech info, he's turned to the alt propulsion field, building in part upon the work of Roy Thornton. This work to date is fully open source and available to the public via his website at stclairtech.tech, which has links to everything he'll be showcasing today. His current work is focused on putting together electric hybrid add-on systems that will operate in virtually any type of vehicle, and his work currently remains freely accessible. So let's welcome Brian to today's event, and I will hand things over to him to get started.
I've got some updates for things that we've been working on here, things that I've been doing. As most people know, I've changed my daytime careers, so I don't have quite as much time to devote to everything that I would like to devote it to. But I do have a PowerPoint that I can bring up and show everybody what's going on, and some of you haven't really been informed as to where all of this came from, so this will help with that a little bit. I'm going to attempt to share my screen here and bring up the PowerPoint. Is that, can you see that, Tim?
Yeah, it looks great.
Terrific. Okay, so as Tim said, I'm Brian Sinclair. I've been doing work in the alternate fields since the 90s. I am an automotive tech by trade. Recently changed over. It's just getting, at this age, a little more difficult to be out in the shop and doing everything that I need to do. Being in the Northeast, it does get just a little bit on the cold side here in the wintertime. So what I want to talk about is the pulsed inertial engine technology, PITech for short. It is indeed based on the work of Roy Thornton. Back in the 1970s, he developed one of the very first systems ever to utilize the planetary gear set that we're still using right now, where we have a stationary gear in the middle and the other two gears orbiting that are the ones that are turning. It is based on that. We've modified it quite a bit. Right there is a picture. It's not a great picture, but it is a picture of the demo unit that Roy would use. He would take around to colleges and potential investors, anybody that wanted to see it, basically, and show them that this is how it works. He was quite open with much of that information. As I said, I've been a full-time professional auto repair for about 40 years now. I'm now switching the career full-time to parts department operations. I've gone to work in a fleet shop, and I'm doing pretty well right there right now. I'm also engaged in the research and development of several of the inertial propulsion systems, as Tim stated. The PI, or pulsed inertial engine, is basically it's a major overhaul of the original work of Roy. He had some things that he never quite worked out, and some other things that I think maybe he did a little better than I would have thought of. So by bringing that all together, I think we've got a system that works actually pretty well. Now we're in the phase of changing that up and integrating some of that with some other technologies that I'm not quite at liberty to talk about yet, but we will touch on that as time goes along. The Trammel engine, or the Pi X as we called it for a while, is it's gotten a new motor, but it's not really ready to be used just yet. The last time I did introduce myself, and this time I just want to give a really quick recap of where we're at with all of this. I have built and tested more than 4 separate, and when I say more than 4, I'm not counting all of the prototypes and the drawing board things, that some of them worked and some of them didn't, and some of them worked, but only if. There was a lot of that only if situation stuff, and I don't count that as truly success, but more than 4 of them that actually did present some results in the reactionless propulsion. I don't really like that terminology of reactionless propulsion, because in reality there is an equal and opposite reaction to every action. We've all been taught that for many years, and it is still true. It's what we do with those reactions and what we do with the energy from those reactions, I think, that is really what makes the difference. A lot of the other designs have been scrapped. Right now we're still working with the original Pi design and still trying to develop. We're making some headway developing the Trammel system. The Pi has progressed from several dozen different design templates, including one very much like Mike Gamble's. I see him on there. Hi, Mike. And you know, there's a lot of different ways to go about getting inertial propulsion. I would rather call it inertial propulsion than reactionless propulsion. To touch on real briefly on Branson Roy Thornton. Roy was born and raised in Manitoba. He was a Canadian inventor that, like I said before, he originated the use of the planetary gear rotating around the stationary sun gear. So many people have put a gear on the outside and attempted to rotate the planet gears on the inside of that. Radical for any government or company to ever really want to do anything with. So it's unfortunate that things went that way for Roy. The original video about Roy and his work is available on my YouTube channel. I've also got a BitChute channel that mirrors the YouTube, more or less anyway. You can just search Sinclair Tech or Grassroots Mechanic Movement, depending on whether you're using YouTube or BitChute. The original video that was shot for Roy was originally, it was on VHS tape, and it degraded a lot before it was digitized. So that it's unfortunate that some of the quality is very poor, but there's still a tremendous amount of awesome information there for anybody that would like to go and see that. Roy built the Ezekiel, he called it the Energy Zone Kinetic Lifter. it used not only the planetary gears set with a weight on each one of the planet gears, but also a magnetic or mechanical braking system that changed the way the weights were allowed to move. As the weights would sling out, he used a brake to keep them in until the right moment and allowed them to sling out and help with his inertial propulsion. It did function, but it relied very heavily on the impact of the weight on the center pin and had tremendous amounts of mechanical losses due to the brakes that he had installed, trying to control how the weight was slung in and out. Similar to that, our system is not allowed to cross center. You can see in the pictures there, the first three on the left, that was the old original Pi 1, which I've still got. It just was so reliable and worked consistently all the time that I don't want to take it apart. I want to keep that around. But we have if we start over on the left, we have that moment of impact when the weight is contacting. The weight contacts the center pin in that center picture of the three. And then the moment that the weight exits that center pin is what he was controlling with his traps, brakes, or whatever he wanted to call them at the time. That was a major difference in how we went about it, in that we put a ramp extension on the end of the weight to control that moment of release. Of course, it has to be timed, so that takes a little bit of finesse, a little bit of R&D as far as when that release is optimal, and therefore how long that ramp is going to be. The photo on the right, that was the very first ramp that we tried. That's also connected to one of the dead blow weights that we developed. He didn't use a stop for the weight when it came around. It would simply sling to the outside, and sometimes it would go beyond that center point, the outermost reach. So that was another thing that we developed that Roy never used. If you look at the four pictures on the right, the very first one was the very earliest, and I mean the earliest. That was the very first set of gears that we ever played with. The weight is literally a nut welded to a bolt, spinning around. So if it spun too many times, it would either wind down or come off. And it literally just had a 17mm socket stuck on the end as the weight itself. But that was the very first time that we saw that this was a viable technology. As we progressed downwards in the photos there, the one at the lower left, that was the four-wheeled Thornson design that if you go to my YouTube channel or my website, you can see that moving across the workbench. It does work. That was the first one that we used that stop on. You can see that they're basically just little pieces of angle that are welded in place to keep that weight from going too far. Those weights were just a piece of pipe with lead poured in the center of them. I mean, very, very crude. But as time went along, we started to get things a little better. The top right one, that was one of the very first. That was the Pi 2.0. That was a double decker in the end. That used a stop that would stop against the center pin. Great design as far as strength. Poor design as far as the fact that would actually sometimes catch on the center pin and not allow rotation to start up. So eventually we came up with the final design. It's adjustable, it's reversible. We can switch that stop around and use it for rotation in either direction, whether it's a right-hand rotation, left-hand rotation. And it simply has a plate with some nuts on it welded to it that are holding a bolt that the weight comes up against. It stops it, and it relays a lot of the kinetic energy directly back into the gear set. And so that was a major improvement over anything that Roy had. Roy had literally some braking systems that would simply hold things in place and then allow it to sling out and spin around when it reached the outer edges. And that was preventing him from building any more power than what he had. The dead blow weight design, I talked about that ever so slightly. The weight is, we decided to try something just as an experiment, and that was to build a weight that was hollow and fill that weight about 3/4 with steel shot. The idea being just like a dead blow hammer, whether you're in carpentry or mechanics, dead blow hammers reduce fatigue on the person using it, and also impart the force of impact better because it keeps the impact sustained a little longer when the hammer contacts the nail or whatever it is that you're hitting. So what we did was we took 3/8 steel bar stock and we made it hollow, filled it up, and then welded the cover on it. That really was a big game changer as well. That's something that was never even intended for the original Ezekiel that Roy Thornton had. Then we moved on to the speed differential control that adds speed to the rotation at exactly the right moment. And when I say exactly the right moment, it's pretty easy to figure that out. It's right when the motor is working the hardest. When the motor works hardest, it tends to slow down. If it is allowed to slow down, we lose 90% of our propulsion. And that was something that was a bit of a difficulty that we had to work out in the very beginning. When we were starting out, we just used a belt to run it, and if the belt wasn't tight enough, we didn't even realize it was slipping. So it was, sometimes it works, sometimes it doesn't. Why is this happening? That was something that we had to work out. We did get it worked out. We run everything off of either a timing belt or a chain now, so there's never a slippage issue. So it became to the point of, hey, what would happen instead of, since it loses propulsion when it slows down at that moment, what would happen if we speed it up at that exact moment? And that's what we tried, and by golly, it sure did work. We were able to control that with a rheostat, with a potentiometer on the speed controller for the motor itself, and just increase the speed enough to bring propulsion back up, allow it to come back to its normal rotation as soon as it left the micro switch, and then do it again at the next moment of needed increase in rotation speed. Eventually, we also tried, as was suggested, Tokyo Muramatsu. He's someone who has worked with me a bit on this. He's worked on some designs of his own. He's got a YouTube channel as well. He actually was the one that said, hey, why don't you try a non-contact proximity sensor? And so I said, well, I don't want to build a humongous proximity sensor system for this. So let's try what we use on our alarm systems for the buildings, and that worked just as well. And we could simply fasten some magnets to the rotating assembly. And when they became close enough to the proximity sensor, that would take the place of the micro switch, and it would simply speed it up and then slow back down when the magnets moved away from it. So I do want to give a big thank you to Tokyo for suggesting that to us. And now we come on to the Mini Pi. The Mini Pi is nothing more than a proof of concept demonstrator. We already know it works. We know what we've got is something that can be used in an automotive or land-based or even an air-based transportation system. I haven't taken it to space, somebody wants to give me the opportunity or take it with them to space, please let me know. I'll supply you with as many of them as you need to take with you. We know it works if we simply install that in a motor vehicle. And so it came to the point where I'm not carrying, 150-pound pi systems into somebody's office to show them how this thing works. Let's build something small enough we can set it on their desk and let it go across the desk. As you can see, it's very, very small. Those are 2-inch gears. So the overall arc is very short. The weight is about 2¼ ounces. So it's very, very small, very light. That overall assembly that you're looking at right there, I'm powering it up off of just a cheap cordless screwdriver that I picked up at one of the tool places. And the overall assembly weighs about 8½ pounds, which is a little much, but most of that weight is in the axles. Considering the fact that we're only moving about 2¼ ounces of weight, and it's able to move an 8-pound unit even a little bit, I'm kind of impressed with that power to weight ratio. So the mini pi, as you can see over on the right, we just simply did a couple of quick little pulleys to make it run off of the cordless screwdriver, and it does work. Is it really useful for propulsion? No, but that is just our little proof of concept demonstrator. Now, as we move on to the Pi X, things got a lot more complicated. We're not really going to go into a lot of the detail on how that works. Over on the right, you see a GIF that is just it's a Trammel of Archimedes. It was known for many, many years as the do-nothing machine because nobody could find an actual practical purpose for it. Now we know that they actually do work quite well for drawing elliptical circles, depending on whether they're a 4-channel, 6-channel, 8-channel, however many slider slots that somebody wants to build it with. They do work, and it took that do-nothing machine and made it a do-something machine. And that's kind of our tongue-in-cheek way of saying, we took some stuff here that wasn't really supposed to work, and we put it together in a little bit different way, and we're starting to see some results from this. So we just kind of called it the Trammel Engine. It is based on some design factors that are not necessarily 100% my own, and because I have made a promise to keep some of those things private for now, that's exactly what we're going to do. There's a picture of the Pi with the Pi X, the Trammel, with the covers on it. As you can see, we've been testing it with a beam attached to the top of it. That's a balance beam assembly. It's 10 feet long with weights hanging off the other end. Because it doesn't have the pivot point, the attachment point directly in the center of the beam, it will tend to balance. And that's exactly what we wanted it to do. We wanted to be able to make the Trammel hover basically on the beam above the workbench so that we can test from there. And we've had some good results. We've had some mediocre results, and we've had some results that were absolutely incredibly inoperative altogether. But it's using something called parallel linear components along with some rotating masses, and it's different. I really kind of wish I could show you the rest of that later on. I'm hoping I can bring on a friend of mine who has worked with me on this. He's working on a machine of his own that is not a Trammel, and it is not a Pi, but it does use a linear propulsion type system. Linear components, and it's more of a training aid than anything else, you know, that we're kind of using to see reaction points in moving linear masses back and forth. If he texts me that he's ready, I'll have him come on for just a minute here at the end, and maybe he can show us where he's at with that. The next thing was that we needed to upgrade the motor for the Trammel. That little motor that you can see in the previous pictures, that little motor right there was only a 350 watt motor, and it only spun at about 350 RPMs. The new motor is a brushless design. It's 1800 watts. It's capable of 5600 RPMs or somewhere in that neighborhood. Came with a matching speed controller, and that really does have enough power. It works quite well. You can see there I've installed the bigger gear. They come with a very small gear because they're made more for go-karts and scooters and such. The difference is it's higher voltage. It's running 48 volts instead of 12 volts. Runs 5200 RPMs, give or take. We've seen it up to 5800. It runs higher power, 1800 watts. It's the brushless design, so it's much more reliable, much more controllable. And because it came with that matching motor controller, we don't have any issues with compatibility. I am kind of getting close to the end of my presentation. I kind of warned Tim ahead of time. I didn't have enough for a full hour, unfortunately. I do want to acknowledge, however, all the terrific folks, Mike being amongst those that have really pushed this technology forward. You know, people like Mike Gamble, Tokyo Muramatsu, Steve Hampton, Sandy Kidd, Mike Marsden, Dean Tesla, and a lot of other visionaries that I'm just not going to go into listing that whole roster off. I do, however, want to give a heartfelt thanks to all of these folks for really pushing this technology forward, and you know, daring to try. I mean, a lot of people just don't dare to try it at all. They think, well, this might work, but then that's as far as it goes. I do want to thank everybody for having me on here. For more information, I do have a website. It's stclairtech.tech. You can email me directly from that web page, or you can email me from an email server directly to stclairtech at stclairtech.tech. That's all I've really got for right now. I appreciate everybody coming on. I don't know if Ross Small is with us, if he's got time to come on and show us anything that he's got going on. Like I said, he's worked with me on this Trammel design for quite some time now. And other than that, well, I appreciate everybody having me on here.
Awesome. So Brian, let me do this. First things first, I'm going to remove Spotlight, and I'm going to stop your screen share there. So everybody, I want to put this thing on gallery view, and everyone, please give an enormous hand to Mr. Brian Sinclair. Brian, thank you for the update, and thank you for kind of the overview as well. Ross is actually here with us, so I'm not sure if he would want to present as well. But you know, why don't we do this first?